everyone. In this video, let us study bivariate expectations and independence. If random variables x and y are independent, then the joint probability separates, that is, fxy of x comma y is equal to fx of x, fy of y. That is, bivariate PDF is equal to the marginal distribution of x random variable multiplied with the marginal distribution of y random variable. Even the bivariate PDF also separates. So therefore, fxy x comma y is equal to fx of x into fy of y. Let us illustrate this with an example. If the bivariate PDF and PDF separate, when we say they are separate only when x and y are independent. For that, let us consider this figure. We'll define the bivariate PDF. The PDF value is equal to 1 for all values of x varying between 0 to 1 and y value varying between 0 to 1. Otherwise, it is 0. Now let us calculate the PDF for x. Fx of x is equal to integral of 1 with respect to y, that is PDF is given to you, varying between 0 to 1, its value is going to be 1, and it is 0 else. PDF for y also can be calculated in the similar way. Fy of y is equal to integral of 1 with respect to x, that value varying from 0 to 1. Its value is going to be 1, and it is 0 else, and this is valid only for a period y value varying from 0 to 1. Therefore, when we multiply these two, fx of x multiplied with fy of y, we get 1 for all values of x varying between 0 to 1, y value varying between 0 to 1, and it is 0 otherwise. So when we multiply fx of x and fy of y, we observe that fx of y, we get the same as that of fxy bivariate PDF. Hence, this bivariate random variable x and y can be considered as independent. We'll take the next example. We consider the figure shown in here. The specific bivariate PDF fxy x comma y is defined as 1 by 4 delta x delta y plus 1 by 4 delta x delta y minus 1 plus 1 by 4 delta x minus 1 delta y minus 1 plus 1 by 4 delta x minus 1 delta of y. Now we need to find fx of x. So we need to integrate fxy with respect to y. When we integrate this with respect to y, we get 1 by 4 delta x plus 1 by 4 delta x and plus 1 by 4 delta x minus 1 plus 1 by 4 delta x minus 1. So when we add these two values, we get 1 by 2 delta x minus 1, and these two values when we add, we get this as 1 by 2 delta x. In the similar way, we can compute fy of y, and when we integrate fxy with respect to x, we get the answer as 1 by 2 delta y plus 1 by 2 delta y minus 1. So when we multiply fx of x with fy of y, we get this as fxy of x comma y. Therefore, we can say that the bivariate random variables x and y are independent. Next topic is of interest is bivariate expectation. Here we have considering a function which is as a function of two variables x and y. So We'll define now the expectation. Expectation of E of x comma y is given by integral of minus infinity to infinity, integral of minus infinity to infinity, g of x comma y, fxy x comma y dx dy. Sometimes this g may be a function of only one random variable. Let us consider the case of it is a function of a random variable x. In that case, we can rewrite this as like this. Integral of minus infinity to infinity dx, integral of minus infinity to infinity fxy x comma y dy dx. And if you observe here, this entire thing, this entire thing is given by fx of x. So therefore, we can simplify this one further as integral of minus infinity to infinity g of x, fx of x dx. So therefore, by definition, we can give one more quantity, we can define one more quantity which is known as correlation. X and y is the expected value of the product x and y, and it is defined as integral of minus infinity to infinity and minus infinity integral of minus infinity to infinity xy fxy of x comma y dx dy. Expectation is conceptually same as aberration. Therefore, we can write the expectation E of xy is almost equivalent to 1 by n summation of I varying from 1 to n x by y. y. Now we have three types of correlation: positive, negative, and uncorrelation. And if the value of 1 by n summation of I varying from 1 to n xi yi, that is expectation of xy, is greater than 0, then we call it as positive correlation. If it is less than 0, it is called as negative correlation. If it is almost equal to 0, then we call it as uncorrelation. If the bivariate random variables do not have means of zero, we generalize the correlation and define a covariance, very important term here. It is denoted by covariance of xy is expectation of x minus mu x and y minus mu y. We try to apply the rules of linear operation to this bivariate random variable. From the previous slide, we know that covariance of x comma y is of xy is defined as expectation of x minus mu x multiplied by y minus mu y. So therefore, we get this as expectation of x into y xy minus mu x into y minus mu y into x plus mu x mu y. That gives you expectation of xy minus mu x expectation of y minus mu y expectation of x plus mu x into mu y. So therefore, if these two are 0, you get this as expectation of xy plus mu x mu y. So if mu x mu y are 0, then the expectation of xy will be same as covariance of xy. If these two happens to be 0, then covariance of xy is same as expectation of xy. If x and y are uncorrelated, then the covariance value is equal to 0. So in this case, when they are uncorrelated, we know that it is equal to 0 e to the expectation of xy plus mu x y. And we know that expectations cannot be negative. So therefore, we have this as mu s y. Thank you. In the next video, let us study correlation in depth.